This is CPE 133. This is description of free-range Verilog Foundation Modeling Chapter 10. And this is Part A, and there'll be several parts of this. So Chapter 10 has to do with ripple carry adders, and it provides a little bit more information on signed numbers. Essentially, it's signed numbers in the context of where signed numbers matter. And if you recall that Verilog does kind of strange things with signed numbers. So there's the disclaimer again. You're not going to learn Verilog by watching videos or reading a book. You actually got to break down and do it. Try some example problems, work in the lab problems. By all means, send me an email if you got them. We are going to deal with ripple carry adders. This is, a foundation module. It's a ripple carry adder. It adds basically two numbers. Now, this is well-known combinatorial circuits, one of the first relatively complex circuits you deal with in a digital design course. And the big issue here, as we'll get to in a second, is that are you dealing with signed or unsigned numbers? So ripple carry adder itself is typically built in two ways, either with all full adders, or we replace the full adder in the least significant bit position with a half adder. So under this case here, if you notice, this doesn't have a carry in. So essentially, for this model right here, which is just a generic ripple carry adder model, we've replaced this half adder with a full adder, which gave us the ability to have a carry in on this thing. So this is low level, this is higher level. We'll be kind of sticking on the high level for this circuit. Verilog has a whole bunch of different arithmetic operators, so one of them being plus and minus, probably the ones we'll use most often because they're pretty straightforward and they're not too complicated as far as the hardware goes. We'll talk about that in a second. Anytime you use any of these other operators, not any of them, but anytime you use these other three operators here, you may want to consider some other issues that we'll talk about in a second. So the issue is when you're using these mathematical operators in Verilog, which means you're modeling hardware, you're going to send your models off to the synthesizer to actually generate some hardware. It kind of feels like programming. These quality operators and the arithmetic operators, they just feel like programming. Even the language itself kind of feels like programming. But the issue is it's not programming. In programming, when you use a plus operator, typically there's going to be some type of hardware, such as in the arithmetic logic unit, that implements the add instruction. So it's no big deal. So if I execute an add instruction in a computer, it's probably already there. I'm not causing the hardware to be more complex. The issue is in Verilog, if I use a mathematical operator, that means the synthesizer is in charge of generating the hardware that can perform that mathematical operation. So always keep that in mind, particularly since not all mathematical operations are created equal. So I mean, certainly if you think about it, there is a relation between multiplying and adding, but certainly multiplying is going to be a little bit more complicated. So the big issues here that we're going to deal with in this chapter is whether the values that we're sending to the RCA are signed or unsigned. Now, it's kind of a funny issue because the hardware doesn't know whether the set of bits you're working with represents a signed or an unsigned number. The hardware just magically works. It's not really magic. It's just based on the representation. There is some work left up to the modelers on this thing, and it's very doable. You just have to know the rules, and so such that you don't allow the synthesizer to do something stupid. Addition and subtraction operators, that's the ones we're going to use most often. And the issue is so Verilog has the notion of signed numbers, and what everyone says is, well, it represents signed numbers using 2's complement notation. It's certainly a great idea because using 2's complement allows for more simple hardware implementations. For example, there's always an issue of an adder and a subtractor. If I have a module that does both adding and if I have a circuit that needs to both add numbers and subtract numbers, what do I do? Do I have separate hardware for the subtractor, or can I just use the adder? So the issue is, particularly when you're working with Verilog and you drop down an operator, you got to really think, did it really generate hardware for that? Or do I really know how it's doing this? You can be pretty positive it's going to do the right thing, but oftentimes you just don't know how it does that. For example, this is the classic subtraction operation, and I can actually rewrite this thing as instead of b minus c, I can say b plus or minus c, which is essentially functionally equivalent. Now the issue here, what makes it really nice, is generating the minus c is extremely simple in hardware, particularly when you're working with the FPGA and some of the tools involved in the FPGA. So it's all kind of the way I look at it is kind of the magic of choose complement notation. It just makes everything work out very nicely. So there are a couple rules to follow, and I actually know what these rules are, and they're really important. I think I almost have them memorized. So the first rule is that the synthesizer is going to look at the entire expression. It's going to look at every single operand in that expression, and it's going to expand those all those values to the operand that has the largest value. So essentially, if I have an expression with operands at different values, all those values are going to be promoted to the operand that has the biggest value. It doesn't really matter which side of the assignment operator the operands appear on. Second thing is, so that essentially that's a synthesizer issue. Okay, so that's important. So the second rule is, I made it purple because it's actually a requirement of designer. So the designer must allow for the appropriate bit width of the signals. Okay, if for example, if you add two 10-bit numbers, you're going to get 11-bit results. If you don't allow for that, your answer is going to be wrong. Now, Verilog is really good at some things, but it still relies on you to provide the we'll say adequate data widths. You know, it's hardware, you're always trying to keep the data as small, like the data width as small as possible to get the job done, but you just absolutely have to make sure you leave enough, we'll say leave enough bits for the result. So the third rule is, you know, certain values, certain operands are going to be expanded in certain cases, and they're expanded based on the signed values. I say the signedness of those values. So essentially, sign extends signed values, and zero extends unsigned values. So in the last rule here is every operand in that expression needs to be signed for it to for the synthesizer to consider the operation a signed operation. So if you have even a single value that is unsigned, it's going to consider the entire operation as unsigned. So this is just our first example. It's an n-bit ripple carry adder, and it's let's do this here. Now this solution is really super clever solution. It's really nice in that manner. It is parameterized. The default parameter is 8 bits, meaning if you don't override that parameter, it will be an 8-bit ripple carry adder. The interesting thing here is the way I've handled this thing. So these are the two values that are essentially being assigned inside the always block, so I did declare them as reges. But the important thing in here is that everything in here was declared as unsigned by lieu of the fact that I didn't put a signed the signed keyword in any of these after any of these input-output specifications. So we're working with unsigned math here. Now, if I look at this equation here, the largest operand is n bits, which is all these three have n bits. And so essentially what's going to happen is these values right here are also going to be expanded to n bits. They're going to be expanded the 0 extension because they're unsigned values. So the issue is this is either 0 or 1, so it still remains a 0 and 1, and this is kind of a special thing. It's being that it's unsigned, it's a single bit, and it's a little bit less worrisome. So the issue here is it's A and B are, it doesn't even know whether A and B are signed or unsigned. You could be sending A or B a signed value. This hardware absolutely doesn't know. This gets extended, so you got 3 n-bit values here. They are added together, and the interesting thing here is how it handles the sum and the carry out. So we did the sum and carry out in one operation, which means the carry out is 1 bit, and it's in the leftmost position because I am using the concatenation operator here, and it's appending it to the sum, which is the n bits on the right side. So the left side is the carry out, the other n bits on the right side is the sum. So this is a very, very clever definition. The nice thing about this is it works for both signed and unsigned values, and so that's super important. So the issue is I know it's kind of a clever design, but if you understand the underlying details on this, you'll get by. And so next, what we're going to do here is look at some issues that will get you in trouble. So this is again kind of shedding light on how to work with signed and unsigned values. Now, obviously, we have a working ripple carry adder, but we want to look at some extra things here.